Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 14 on additional triangle proof. This is our last lesson in Unit 3, which is concentrated on how to prove triangles are congruent and what other kind of conclusions we can make if we can prove triangles are congruent. And we've seen all sorts of things involved. We have all of our triangle congruence theorems. We saw things like parallel lines get involved, all across the board. All we're going to do in today's lesson is a few additional proofs. I think we have 3 in total, one of which is quite long, and that's going to be the point, right? And the other 2 are kind of just there to sort of get other ideas involved that we've seen throughout, but we want to refresh one last time. So let's jump right into it and get into these additional proofs. So we're going to start with a lengthy proof, the lengthiest proof that we've had so far. Now we've seen many methods for proving triangles are congruent: SSS, SAS, ASA, AAS, and our last one, hypotenuse leg, HL. We've also seen how to use CP/CTC reasoning after we have proven triangles are congruent to then show that two sides or angles are congruent. In general, you'll always need to decide which methods apply in a given proof, right? So, we've had a day on side, 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 a day on side, angle, side, etc. But you'll be having to make that decision for yourself. And sometimes you may even be faced with a very lengthy proof. So let's start in exercise 1 with one of those longer proofs. In the diagram, it is given that EAF, EBD, FCD, segment ED is congruent to segment FD, segment EB is congruent to segment FC, and segment DA bisects segment EF. Prove that triangle BAD is congruent to triangle CAD. Letter A. Sketch a diagram of how you will go about doing this proof or describe your strategy. Understand what each given tells you and work backwards if necessary to understand what you will need. Okay, wow. Well, what I'd like you to do right now is pause the video, all right? Really take a look at all your givens, mark them up as much as you can. Make sure to really look at your end goal, right? Triangle BAD congruent to triangle CAD, and think about what your strategy might be. And it's going to be a multi-pronged strategy because this is probably going to be, let's say, maybe around a 13-line proof. So pause the video now and do some thinking about this. All right, first thing I think I'm going to do is I'm going to outline the 2 triangles that I'm trying to prove congruent so that I never lose sight of my end goal. Always a little bit dangerous if you don't start by really understanding what you're trying to prove congruent. So I'm trying to prove that triangle BAD, which is right here, is congruent to triangle CAD. All right. Let's go back. Whoop, definitely don't want green. Let's go back and start to mark up our givens. So we got to keep this in sharp focus. Now, our first 3 givens are just collinear givens, right? EAF is collinear, EBD collinear, FCD collinear. No real way to mark those up, but important to know. And also important to note, they probably put those there for a reason. All right. Now let's take a look. The first real given we can work with is the fact that ED, right, is congruent to FD. Now, one thing that's a little bit tough about that particular given is it's a little bit hard to mark up, right? Because of the fact that we've got these intermediate points like B and C, it's hard to mark that ED is congruent to FD. So I often do it kind of like this. Maybe it's not the best method, but it's all I got. All right. Now we also know that EB is congruent to FC. I'll put a single dash mark out here just to kind of indicate that that's what I was marking. All right, I know that DA bisects EF, so that's going to tell me that EA is congruent to FA. All right, wow, that's it. A whole bunch of sides congruent to each other, but not much more. Now, let's think about a little bit about what we can do, okay? One thing that I could do is the fact that these 2 longer sides are equal and two shorter sides are equal that are parts of the longer side, I should be able to do subtraction to prove that BD is congruent to CD. So, right, I can use a subtraction. Subtraction is going to allow me to eventually prove that BD is congruent to CD. And that's important because BD and CD are parts of the triangles that I'm trying to prove congruent, right? So I can eventually get that these two are congruent, right? Maybe 1, 2, 3, 4, 1, 2, 3, 4. Wow, that's a lot. Now, what else can I do? Well, you know, in terms of the two triangles that I know are congruent, I can 2, 3, 4, 5. They also share side AD, right? That's just that reflexive property. So that's simple enough. But I don't have anything else, right? That's all I have right now. Now, there is one other thing though. The fact that ED is congruent to FD tells me that the large triangle here is an isosceles triangle. And because it's isosceles, I'll be able to prove that these two angles are congruent because the base angles of a triangle are congruent. So the fact that, you know, ED is congruent to FD, right? That will allow me to prove that angle E is congruent to angle F, right? That's that whole base angles of an isosceles triangle are congruent. But now, take a look, right? Based on the fact that, right, the givens that I already know, and this fact, I'll be able to prove that triangle EAB is congruent to triangle FAC by side angle side, right? And those are these two triangles right here, these two smaller triangles. Now, once I know those two triangles are congruent, I could then, that's right, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, I could then prove that AB is going to be congruent to AC by CPCTC, right? And that's now going to allow me to prove that the two triangles I actually care about are congruent by, of all things, side, side, side. Now, there's a lot of work here, right? One piece is just proving that these two little triangles are congruent. That shouldn't be too bad, right? Because most of that is just givens. The one non-given part is the fact that angle E is congruent to angle F by that whole, you know, base angles of a isosceles triangle are congruent, right? Once I have those two little triangles congruent, I can certainly conclude that AB is congruent to AC by CPCTC. Maybe the hardest part of this proof will be to take the fact that ED and FD are congruent and subtract out EB and FC in order to get BD congruent to CD, right? Because that's going to be a partition proof, and you know, no matter how you spin it, when you put a partition proof inside of a longer proof, it adds like, I don't know, 4 or 5 lines, you know, depending on how you break it down, all right? But we have the general idea. We're going to have to do a subtraction proof to get BD and CD congruent, right? We're going to have to conclude that the base angles of this isosceles triangle are congruent in order to prove that the two small triangles here are congruent. Once we have those, we can use CPCTC to prove these two are congruent, and then we've got these two triangles congruent by side, side, side. It's lengthy though. There's quite a bit in there that I haven't like really exactly spelled out, but it's mostly there, okay? I've even drawn the diagram twice here because as we kind of do out the proof, we're going to want it. All right, pause the video now and see if you can write out this proof. All right, are you ready? Well, the beginning of it's going to be easy because you know that there's going to be some givens. So I'm going to get those 3 collinear givens written down. And those, especially the second two, are really important for the partition part of the proof. Without actually having these two down, you can't really do the whole partitioning thing. You've got to know that they're collinear. All right, let's also get those other 2 givens down. I suppose I should get both of those in. Now, once we have that, there's only one other given, all right, and that's DA bisects EF. So 3 of those lines are just given, and again, you could lump them all together and then say given just once. Now, where are we going to go from the givens? Well, first, let's take the easy one. The fact that EA is congruent to FA, right? Now that was based on the fact that DA bisects EF, so my reason, a bisector divides a segment into two congruent segments. All right, great. Now I can say that angle E is congruent to angle F, right? Now, why was that? Well, that was based on the fact that the base angles of an isosceles triangle are congruent. Simple enough, right? Now, we really have enough, given that we already know that EB is congruent to FC, right? We now have enough to conclude that those two small triangles are congruent. In fact, I'm now going to say that triangle EAB is congruent to triangle FAC, and that's simply based on the SAS congruence theorem. All right, now I'm going to shift the board up a little bit. But keep in mind, where we've gotten so far is that these two small triangles are congruent. Awesome. Okay, so now that we know those two triangles are congruent, right, I'm going to use CPCTC to then conclude that AB is congruent to AC, right? That's where we're right here. Now we're starting to work into the two triangles that we want to know are congruent, or we want to prove are congruent. All right, now AD is congruent to AD, right? That's my easy, that's my reflexive property, right? Now the only piece that's left is to do that partition proof, right? And somehow subtract out the EB and the FC, right? In order to get the BD congruent to CD. That's going to take a little work. First thing I need to do is break up those holes. So in other words, ED is equal to EB plus BD, and FD is equal to FC plus CD. That is, of course, just the partition property. Now, one thing that's a little tricky, right, is that all of my givens are way up here, right? And right now, I've got this given way up in number 2 that says ED is congruent to FD, and I'm going to substitute these two things into that given. And it's a little unfortunate that that given is way up here, but I needed to have it up here in order to conclude that the base angles of an isosceles triangle are congruent. But now I'm just going to substitute those things into that given from way up above, and then that's the substitution property. Now, remember, I already know from up above that EB and FC are congruent, right? We know that these two are congruent. It is literally the given that's sitting right here. So now I'm going to take this given and I'm going to subtract it from this line right here. I'm not going to write it down again, although you could. And I'm going to get BD is congruent to CD by the subtraction property. By the way, I have no problem with people writing that given down again. And there's nothing wrong with writing a given more than once, especially if it helps you see the subtraction. All right, but you don't need to write it again. I literally subtracted that away from here. That gave me the fact that BD was congruent to CD. And now our final line, triangle BAD is congruent to triangle CAD by the side-side-side congruence theorem. All right, and again, depending on how you spin this proof, whether you write down, these two in 2 lines instead of 1 line, depending on how many lines you use to write down the givens and whatnot, this could be a much longer proof, right? This thing could range as large as like 16 or 17 lines long if you start to separate things a little bit more. But some geometry proof can be quite long. Now, my guess is you won't have to do too many that are this long, and there's a, kind of a 50-50 shot that you could get a really long one like this on a state exam, let's say. But you should be prepared for it, and it's all about just following logic and using what you already know. All right, the other 2 proofs that we're going to do in this lesson aren't going to be nearly this long. I just wanted to make sure we did them to highlight some other aspects of proof that we've been seeing all along, but that I wanted you to see one more time. Let's take a look at our next proof. All right. We should be ready to use properties of angles created by parallel lines within geometry proof. And we spent an entire lesson on doing exactly that. But I wanted to do it one more time in our final day on geometry proof. You can already tell this is going to be a much shorter proof because my t-table is much smaller. Let's take a look at exercise number 2. Given segment AEF, segment AF bisects angle BAC, And DE, segment DE, is parallel to segment AB. Prove that triangle ADE is isosceles. Fantastic. Okay, what I'd like you to do is pause the video now, mark up givens and things like that, and think a little bit about how you can possibly prove that triangle ADE is an isosceles triangle. See if you can figure out the strategy. All right, well, that first given is a collinear given, so we're just going to kind of move on from that for right now. AF bisects angle BAC. That's easy enough to do, right? That's going to tell us that this angle is congruent to this angle. All right, simple enough. Whoops, I can't get this to unhighlight. There we go. All right, and we know that DE is parallel to AB. In other words, this is parallel to this. Okay. Well, that doesn't tell me too much, right? But keep in mind that what I'm trying to do, and let me again outline it in using a highlighter, is I'd really like to prove that that is an isosceles triangle. Now, an isosceles triangle, by definition, is a triangle that has two sides that are congruent. Now, if I can prove that two angles in the triangle are congruent, then of course I can prove that two side lengths are congruent because sides opposite congruent angles are congruent. Well, right now all I know is that this angle, BAE, is congruent to this angle, DAE. What I'd really like is DAE to be congruent to DEA. I'd love these two angles to be congruent. Now, why in the world would those two angles be congruent? Well, right, I know that this line is parallel to this line and is cut by this transversal, which means that this angle must be congruent to this angle, right, because they're alternate interior angles, right? And if this angle is congruent to this angle, and if this angle is congruent to that angle, then I can say that these two angles are congruent by substitution. And once I know those two angles are congruent, I can say that sides opposite of those angles are also congruent. All right? It looks almost like it's like a double arc mark there. It's just a single arc with a single slash. All right. Pause the video now and see if you can get this proof down. All right, so let's go through it. Here we go. AEF and AF bisects BAC. Simple enough, given. I'll get that other given down in the next line. I could lump them all together. Sometimes I choose to lump two together and let one just kind of hang out on its own. All right, so now I know that angle BAE is congruent to angle CAE, and that's due to the fact that a bisector divides an angle into two congruent angles. Okay, simple enough. Now, I can also say that BAE is congruent to DEA. Now remember, that's BAE is congruent to DEA, and that is because of that parallel line business. Alternate interior angles created by parallel lines are congruent. Now again, notice, BAE is congruent to CAE, and BAE is congruent to DEA. That means now that I can say that angle CAE is congruent to angle DEA by the substitution property. Now that I've got those two angles congruent, right, the one here and the one here, I can now say that AD is congruent to ED because sides in a triangle opposite congruent angles are congruent, right? That's very important, that wording. Sides in a triangle opposite congruent angles are congruent. Make sure you've got that in a triangle. You don't want to just say sides opposite congruent angles are congruent. And you certainly don't want to say base angles of an isosceles triangle are congruent. This is actually kind of the reverse of that. But once I have that AD and ED are congruent, I can now say that triangle ADE is isosceles by the definition of an isosceles triangle. Or you could say because any triangle that has two congruent sides must be isosceles. All right. And it's really cool because we have two things going on here, right? We've got parallel line properties and the angles that they tell us are congruent. But we also have the idea that if we have a triangle where two angles are congruent, right, that's line 5, we can then conclude that the sides opposite of those two congruent angles are also congruent, right? So two important principles in this proof. Why don't you pause the video now and write down any lines of this proof that you need to. All right, let's do one final one. Oh, I'm going to miss triangle proof. Don't worry. We're going to do more of it in the next unit, and even more of it then in Unit 6. I think it's Unit 6 before we revisit it. All right, so the final little piece is something that we've seen in many proofs so far, auxiliary lines, all right, or extra lines. I think the Latin literally means helping lines, okay? Sometimes a line must be added to a geometric diagram to help prove something about the original diagram. These are known as auxiliary lines, which we've seen a few times before. I think this might be like the 5th or 6th time that we've seen them. So these aren't brand new, and that isn't the first time we've seen that pop out. Man, I tell you, if anybody knows how to get rid of that, send me an email. Let's take a look at exercise number 3. Given that segment QP is congruent to segment RS and segment QR is congruent to segment PS, prove that segment QR is parallel to segment PS and segment QP is parallel to segment RS. All right, so this is all we know about this quadrilateral. And in Unit 6, we're going to be studying quadrilaterals a lot. So auxiliary lines are going to be very important there, okay? And we need to somehow prove that the opposite sides are parallel to each other. Letter A. Why can we not use a triangle congruence theorem yet to help us do this proof? Well, state the obvious. Pause the video now. Well, the obvious is there are no triangles, right? It's pretty hard to use a triangle congruence theorem in an image or in a figure that has no triangles, right? So it's that simple. There are no triangles. And that can be very deceptive for people, right? Here I've got a figure, right? It's a quadrilateral. And there's no triangles, so how would I use a triangle congruence theorem to help prove that sides are parallel to one another when there are no triangles? All right, so let's take a look at letter B. What segment or segments would make sense to draw in as an auxiliary line to help with the proof? Why? Draw the segment or segments. Pause the video now and think about this a little bit. Well, you might already be able to see down here a little bit of it. But basically, if I draw in either one of the diagonals, either one of them. Now, sometimes we may even want to draw in both of the diagonals. But here, it really just makes sense to draw in one or the other, right? So I'm going to draw in either diagonal. Either diagonal. Because it will create two triangles. Whoa! It will create two triangles. Now, the only problem with drawing in, let's say, the second diagonal at the same time is that now I really have 4 triangles. Right, and that's going to be harder to work with. Plus, it's going to be trickier to really understand what I have, right? We don't know anything about these diagonals and what they're doing, so it gets a little bit trickier now to kind of figure out what's going on. Okay, so I'm gonna delete. I like how I said that. I'm going to delete one of the diagonals. I'm not saying that both diagonals can't be used, but it's simple enough to just use one diagonal. So letter C, do the proof below. All right, what I want you to do is pause the video now with one of the two diagonals drawn in. Probably you want QS just so that we can have exactly the same proof up here. And I'd like to see if you can come up with a strategy for how to go from here, right? And I've marked up all the givens that we know already. Somehow we can go from here to proving that QR is parallel to PS and that QP is parallel to RS. Pause the video now and see if you can just figure out the strategy. Well, what's really cool, right, is as soon as I draw that diagonal in, given that the diagonal is a shared side between the two triangles, we can now easily see that this triangle is going to be congruent to that triangle by side, 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 the least used of all of our congruence theorems. Now, once we know that those two triangles are congruent, we could certainly then say, I'm going to mark this in red, we could certainly say by CPCTC that these two angles are congruent, right? And once we have those two angles congruent, we can then show that QR is parallel to PS because alternate interior angles are congruent. And likewise, maybe a little bit harder to see, we can then show that this angle is congruent to this angle, also by CPCTC. And then QP must be parallel to RS, again for the same reason. Alternate interior angles are congruent, and therefore lines must be parallel. I'd like you to pause the video now and see if you can work through this proof. All right, let's do it. This is actually not the longest proof out there. That was our first one. So QP is congruent to RS, given. Maybe make it a little longer. I'll put the two givens in two different statements. Given. All right. Now that was just our two givens. Let's get that third side congruent to itself by the reflexive property. And that's all it will take now to determine that triangle PQS is congruent to triangle RSQ by the side, side, side congruence theorem. All right, now I've got those two triangles congruent. Now I can get to town, right? Now I can say that angle PQS is congruent to angle RSQ. Those are actually the double arc marked ones. That's CPCTC. We could also conclude that, that angle PSQ is congruent to angle RQS. Those are the single arcs, also by CPCTC. Now again, you could lump those two together since they have the same reason, but now we're ready for it. We can actually go for our last line, which is that QR is parallel to PS and QP is parallel to RS because, let me get this out of the way, if alternate interior angles are congruent, then the lines are parallel, right? As soon as we know a pair of alternate interior angles are congruent, then we can say that the lines are parallel. And again, this one has so many beautiful pieces to it, this proof, even though it's relatively short, right? But the big piece was the idea that we started with a quadrilateral, right? We started with a quadrilateral that had no triangles whatsoever in it, and we knew that the opposite sides were congruent to each other, and by drawing in a single extra line segment, that allowed us to then prove that these two triangles were congruent. Because we could prove those two triangles were congruent, we could then prove that those angle pairs were congruent, and because we knew that, we could then prove that sides were parallel to each other. All right, let me bring this up just a little bit so you can see it better. Pause the video now, write down any of these that you need to, and then we'll wrap it up. All right, well, this makes me a little sad, right? And it makes me a little sad because we're done with Unit 3. And Unit 3 is what most people remember about their geometry class. If you ask your parents, what do you remember about geometry? They'll probably go, I remember doing a lot of proofs, a lot of T-table proofs, And that was what we concentrated on in this unit. And there are a lot of big pictures we saw in this unit. Primarily the idea, though, that you could have a limited amount of information about two triangles and allow you to conclude that those two triangles were identical. And once you knew those triangles were identical, you could then use that fact to then say that parts or corresponding parts of the two triangles were also congruent, right? From that, we were able to then, come up with a lot of interesting and important geometric results. And again, too many for me to go through in this summary now. Now we're going to see triangle proof, very simple triangle proof, come up in the next unit when we do what are called constructions. And 2 units from now, in Unit 6, when we start looking at quadrilaterals like parallelograms and trapezoids and rectangles and rhombi and squares and all of that, triangle proof will also rear its ugly or beautiful head, depending on how you like it or don't, right? It'll rear its head up again in order to prove various things about those figures. In fact, the last proof we did essentially was to prove that a 4-sided figure with opposite sides of the same length is a parallelogram. But we'll revisit that a few units from now. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.